and get started.
Okay, hello everyone. I'm Matthew Temple. I'm currently at UDP in Santiago, and today I'd like to talk about some work I've recently submitted with Paul Hewitt and Amanda Banerjee, looking at modeling type 1 quasar colors, and specifically in the era of Rubin LSST. The submitted version of the paper is on the LSST Slack. If anyone wants a preprint copy and doesn't have access to Slack, do feel free to email me. So by way of motivation, right, sort of what do we expect luminous AGN or quasars to look like in LSST, or more specifically, how might they be different from currently known populations of quasars, such as the ones that we see in SDSS? And so the motivation behind the work today is, how can we predict the colors that of objects in SDSS that we might expect to find, and specifically as a function of their redshift and luminosity? And what other parameters might be important aside from redshift and luminosity? And to, as a bit of a spoiler, I think Amanda mentioned this earlier, right? There's sort of the emission line properties and the host galaxy contribution as well. So sort of as an introduction, right, there's lots of existing composite spectra or templates in the literature, right? And so why can't we just use those? And the problem is that existing spectra or composites effectively provide a single model or a single prediction for some given redshift or some given luminosity or some given flux limit. And so this is the Vandenberg 2001 composite spectrum, which is highly cited. The trouble with this is it was obtained using observed frame optical SDSS spectra for quasars at a large range of redshift, right? So what this means is that the rest frame optical pixels in this composite are coming from low redshift objects, whereas the rest frame UV pixels in this composite are coming from much higher redshift objects. And obviously these objects are significantly different luminosity because of the early SDSS flux limit. And we can see this sort of by comparison with the Salsing 2016 composite, which was is also gaining some traction, and that was formed using X-shooter spectra of very luminous quasars, all at redshift 2, right? So these are very bright objects, all at the same redshift. And you can see it agrees quite well with the Vandenberg in the sort of 2,000, 3,000, 4,000 angstrom range. But at very short wavelengths, there's quite a significant difference in flux, which is actually due to the IgM Lyman transmission. And at long wavelengths in the rest frame optical, there's a significant change in the continuum slope. And this is actually due to the difference in luminosity, which is driven by the difference in redshift combined with the flux limit. But actually the fact that the low redshift objects in this Vandenberg composite have got much more contamination from the host galaxy. And just to emphasize, so this is on a log scale on the y-axis. So actually this is quite a significant difference in flux. So what we'd like to do is construct a model for quasar SEDs, or indeed colors, which can account for changes in luminosity or flux, as well as just the redshift shift. And something else to think about, and this is a sort of shameless plug for a paper I recently had accepted with Gary Furland and Paul Hewitt and others, is the fact that the emission lines within the population can display a huge diversity, right? So this is the rest frame ultraviolet wavelength range from sort of Lyman alpha through to carbon 3. And plotted here are two composite spectra of real objects. These are composites of real SDSS quasars, where in red we have objects with very strong high equivalent width emission lines selected using the carbon-4 complex, and in blue we have objects with much weaker carbon-4. This also happens to be blue shifted. And we can see that this correlates with changes in other emission lines, especially in Lyman alpha. Again, this is a log scale on the y-axis, so we've got huge changes in the amount of flux in these lines. And the question is, well, why should we care about this? And the answer is because this has an effect on the broadband photometry. So taking a similar sample of SDSS quasars, where we have emission line measurements covering carbon-4 across sort of redshift 1.5 through to 3.2. And matching in flux, so there's no luminosity dependent changes here. In red, I'm showing the sample of strong lined objects, and in blue, I'm showing the sample of weak lined objects. And the points are just showing the median color UGRIZ from the SGSS photometry, with the error bars displaying the scatter within each redshift bin. Right, so this is all observed data. And we can see that just selecting on one emission line gives quite significant changes, sort of up to 0.1 magnitudes in different colors, based on the fact that the emission lines are correlated with each other. And so ideally, any sort of model for the photometry that we're going to get with LSST needs to have the ability to account for these changes. So what are we doing here? We're trying to construct a parametric SED model for quasars, and indeed other AGN, where the parameters are sort of able to evolve in a sensible way that is informed by known astrophysics, right? And initially, we're seeking to reproduce the average colors of known populations as a function of luminosity and redshift, but also, we want to then use that to inform and make predictions for new populations, fainter populations, such as will be discovered with LSST. Worth saying that this model could also be used to examine individual objects, and Manda talked a little bit about this in her talk earlier, not only for photometric redshifts, but also for investigating other properties of individual objects. I don't really have time to talk about that today. So what's going into this model? We've got a continuum, which is effectively a set of power laws from around 900 angstroms through to 3 microns, so covering the rest frame, UV, optical, and just peeking into the near infrared. We add in a hot dust blackbody, which accounts for the near infrared excess due to sublimation temperature dust, and also the Lyman suppression due to the intergalactic medium, high redshifts. We have the facility for dust reddening, although I won't talk about that too much today. I'm happy to take questions if people have questions about dust. But then the two things that are sort of really new for this model, we take a set of emission line templates where we use a single parameter to account for the sort of correlated emission line properties that I talked about a couple of slides ago. And we also include a host galaxy component to the model, which we allow to vary the luminosity. And so both the emission line templates and the host galaxy contribution are varying smoothly with the quasar luminosity. And this is, I should stress, this is very much in an average sense. This is looking at the average properties of quasar colors as a function of luminosity. Obviously, there's still going to be scatter and variance within the population. I should also say, we're using an S0 galaxy template for now, but it's very easy to change that or use a different galaxy template if that's what you want to do. So I guess just a little bit more about the emission lines. Effectively, this is the same, on the top left here is the same panel I showed earlier with the rest stream ultraviolet, and what we do is we extend that into the rest stream optical. And specifically, we're looking at strong lines like H alpha or H beta and the oxygen 3. We know that the emission line properties are correlated across the ultraviolet to optical. So what we do is we construct these templates to match the known properties of existing populations. So what do I mean by that? Well, specifically, this is using the catalog from Liam Copeman, this 2019 paper, where on the x-axis here, we've got the strength of the carbon-4 line, and on the y-axis, we've got the strength of H alpha in blue and the strength of oxygen 3 in black, and each cross represents an individual object. And both the oxygen 3 and the H alpha properties are correlated, right? And so we effectively construct the emission line template so that using a single parameter, we can reproduce these correlations. And this is especially important for H alpha, where, going from weak lined objects where the H alpha equivalent width might be sort of 200 angstroms up to maybe 600-700 angstroms in strong lined objects, is going to have a significant effect on the colors in any photometric survey. So now that we've got the model sort of set up, we need to sort of calibrate the model parameters. And so what we do, we're very careful to calibrate the model parameters using a wide range of redshift and indeed flux. So in the figure here, I'm showing some of the flux bins that we use to calibrate the model parameters. It's using the SDSS DR16 quasar catalog. We effectively take all of the objects from redshift 0.2 out to about redshift 4. The solid lines here are representing the observed data. So again, as with the plot I showed earlier, the solid lines are showing the observed average color within each redshift bin, and the error bars are showing the observed scatter within every 8th flux bin this time. And in green, I'm showing a fainter population, and in orange, I'm showing a brighter population. And you can see especially from this is the SDSS, GGRIZ, and the WISE W1, W2 colors. Especially in the WISE W1, W2, there's quite significant changes in the observed colors, which we interpret and is very consistent with changes due to the strength of the host galaxy. So the squares here are showing our calibrated model for these redshift flux bins. And you can see that the calibrated model is doing a very good job of matching the observed data across a wide range of redshift and indeed both flux bins. At low redshift, there are also changes in the host galaxy, and then you can see, for example, there's slight changes in the strength of this wiggle due to the strength of the H alpha emission line moving through the different passbands. For those who sort of think about SEDs in a more traditional sense, this is just an example in a sort of classic wavelength flux plot, where for reference, I'm showing the SDSS. These are actually the UKIDS passbands and the WISE W1, W2, although the VISTA passbands are very similar. And going from sort of redshift 0.5 down to redshift 3.5, there's obviously the effect of the redshift shifting the different emission lines, different features through the passbands. But there's also, on average, higher redshift quasars are brighter. They have a smaller contribution from the galaxy, so you see a much sharper dip in the 1 micron inflection point here. And there's also changes in the emission lines. Brighter quasars tend to show weaker lines. You can see that the H alpha, so H beta to oxygen 3 line ratio is quite different in these two model SEDs. So before we make predictions for LSST, right, we'd like to check that our calibrated model is doing sensible things. And so this is just a sanity check that effectively taking our model and making predictions for known populations that haven't been used to constrain the model parameters, we still get sensible results. And so here I'm showing, again, the solid lines are showing observed data. This is the observed colors of SDSS quasars in the VISTA Viking survey with Z, YJH, and Z minus H colors as the function of redshift. And this is probing 2.5 magnitudes deeper and fainter than the populations that were used to constrain the model. And again, we can see that as we go fainter, as you go blue to orange to green, the Z minus H colors get a lot redder. This is because the effect of the galaxy coming in, the stronger host galaxy in fainter objects. And again, the squares are showing the model color, where this time this is a predicted model. This hasn't been fit to these data at all. And somewhat reassuringly, right, that the model reproduces the data. We can see the change in the colors, and it's well within the observed error bars. So this gives us confidence.
Matt, you got about 3 minutes.
Perfect, thank you. This gives us confidence that we can take our model and make predictions for Rubin LSST. We've only used objects that are brighter than an absolute Ibag magnitude of -22 to constrain the model. So we've limited our predictions to that luminosity limit for now, which is about 10 to the 44.5 ergs per second. And so what I'm showing in the plot here, again, as a function of redshift, this is now LSST UGRIZY filters. And this is what we expect the average unreddened colors of quasars to change, like going from sort of 19.5, which is what we might, what we've already got from SDSS, down to I of 24, which is sort of the LSST single epoch limiting magnitude. And we can see there's, there's some changes in the strength of the emission lines, and indeed at low redshift, the host galaxy. And this is obviously going to become more important as you go fainter. And in case it wasn't obvious from John's talk earlier, right, this clearly has implications for morphology selection. You can't be selecting AGN by assuming they're all point sources in the 2020s. Perhaps just to motivate this, the need for infrared data, this is now showing the same principle, but with the Euclid YJHK colors. And you can see that the changes in color as you go fainter are much more obvious in the Euclid passbands, sort of up to 0.2 magnitudes. And that again is driven by changes in the galaxy contribution. So if we have this near infrared data, that gives us a much better handle on what we can do in the Rubin passbands to disentangle the AGN emission from the host galaxy. So just to summarize, hopefully I've convinced you that parametric quasar SED models are not only useful, but also necessary, not only for investigating the average properties of different subpopulations, but also the variance within those populations, and that we can then extrapolate down to new and upcoming surveys like LSST to make predictions for as yet undiscovered objects. There is also scope to use them for investigating individual objects. More specifically for LSST, we expect the fainter populations will have, on average, different emission line properties, and on average, more contribution from the host galaxy, which will need to be accounted for in selection, well, both selection and also science investigations. And with that, I'm happy to take questions.
Great, thanks, Matthew. I think I saw a hand from Michael Strauss.
Hi, just given the talk that we just heard from John about separating the AGN and the host galaxy contribution, I mean, you have taken the host galaxy plus AGN together. I'd be interested in hearing your thoughts on sort of the pros and cons of trying to separate things morphologically and then do the SEDs separately versus using the summed light, which is, I think, the approach that you're taking.
It is. So I've assumed, yeah, the data I've been using so far is SJSS, UKIDS, WISE, and Vista, which has obviously got a much broader PSF than anything with HSC or indeed LSST. I think there's clearly scope for both methods. I think both have, useful things to add. I think I'm cautious about relying on deblending images because, as John said, it's a hard problem. And I think, basically all of the objects that I've looked at were selected as point sources in SDSS, and we're finding that they might have 10, 20% of their flux coming from the galaxy, right? And so, yes, LSST is a much bigger telescope. We're going to have much higher quality imaging, but at the faint end, where the new discovery space is, things are still going to be fuzzy. And so, I'd argue that for the most, perhaps the biggest discovery space at the fainter end, we need to be doing both and thinking very carefully about what we can do and where we can get the biggest bang for our buck, if that makes sense.
Mm-hmm. Yeah, I imagine that if you're folding in WISE data, for example, where you're never going to have the morphological information to do that separation, I think that will be also important. Thank you.
Yeah, exactly.
Matthew Graham.
Yeah, nice talk, Matthew. So my question is, I mean, you're making this point that the faint quasar populations may have different emission line properties, and the effect that has on the broadband photometry. Does that mean we should expect to see different variable properties from that fainter population as well?
Yes. I mean, variability is not my area of expertise, but I get the sense that even within the AGN science collaboration, right, the variability subgroups and the sort of high redshift luminous subgroups are not always talking to each other as much as they could. I think a lot of the objects I'm looking at, or that certainly we know that luminous objects are less likely to vary, right? And that's whether the emission line properties are driven by the pure luminosity or by the Eddington fraction is still an open question. I think there's some evidence that the Eddington fraction is probably more of a driver. And so when we're going fainter, we perhaps need to be asking, are we picking up smaller black holes with the same, Eddington fractions, or are we picking up bigger black holes that have got lower accretion rates? And I think that's a really interesting science question that we can and should be addressing. And yes, variability will have a role to play in that, as well as the broadband colors and the emission line properties. If that answers the question.
Yeah, it does. Thanks.
I'll say Weixiang will talk about this afternoon too, and then maybe this is a good topic for discussion. But I would say yes, absolutely. The extreme of the emission lines should have fairly different variability that we can and should take advantage of. All right, Matthew, anything else? Either Matthew, anything else on that? Or
no.
Let Mara Salvato?
Yeah, great talk. I really appreciate it. I have a comment and a question. The comment, please don't take it as a bragging, but I really would like that you look the talk that Gordon was mentioning on the photosys. I made a long review for the CD fitting like a few months ago in the photosy LSST group, and I am touching on many of the points that you are also mentioning. And the question is, instead of spending time on repeating some of the old work, you could really spend energy in improving on some of the things that you're doing, because you're really doing a great job. And the question is on the host galaxy that you're using an S0, and you are saying that you can change the host. So the S0 has the plus that there is no star formation. But at the moment in which you are working on the local universe, where many of the AGN are actually ciphers that are hosted in galaxies that are also star forming, you also need to take into account the emission from the emission line from the host, and they also follow certain rules depending on the type of the galaxy. So how are you going to tackle that issue in addition to the emission for the quasar?
Yeah, that's very good points. In terms of the S0, there's no particular physical reason why we've chosen that galaxy. It just happens to provide the best fit to the observed SDSS colors of the SDSS quasar population, which is inherently bright.
So the reason why it does that is because usual quasar are in the most passive massive objects. So S0 is the ideal template, but in the local universe you have ciphers.
I'm not sure whether we know that's the case in the sense that at the moment, most of the constraining power in the photometry is coming from the sort of rest frame 1 micron region, where the quasar the sort of naked quasar SED is reaching a minimum, right? And so we can get a reasonable handle on the emission from the old stellar populations, but in the UV end, the brightest AGN are going to be outshining the host galaxies in the UV, which is where we have the information about the young stellar populations. And so yes, for the data I've currently used with the existing sort of redshift 2, 3, 4 quasar populations, we can't really say what's going on with the host galaxy and the rest stream UV, given just the photometry. And absolutely, going into LSST, we need to be thinking about young stellar populations, different galaxy templates, and what effect will that have on the broadband colors, and can we separate out using variability? So yes, absolutely, we need to be doing this. I completely agree.
Thanks.
Okay, thanks everyone for the questions and Matthew for a great talk. We should move on. So I have dropped the recording of Mara's talk from last spring into the chat. I will discourage anybody from going off and watching it now because it's an hour. But you know, perhaps if people have time to watch it sometime before the meeting ends, you know, we can add it to our topics of discussion in one of the afternoons. Okay, so I will turn things over to Matthew Graham from Caltech, who's going to give us a deeper perspective of quasar variability.
Okay, thanks, Gordon. Hope you can see my slides.
Yes.
Yep. Okay. So yes, I want to offer a sort of deeper perspective in a number of ways on AGN variability. I'm here as, I'm an associate member of the AGN group, but I'm also a member of the Informatics and Statistics Science Collaboration. And so a lot of my day-to-day work is sort of thinking about time series problems in general. We know that quasars are the baddest and the weirdest, but the variability, their variability is also one of the most unexplained phenomena. You go back to the 1963 paper by Sandage and Greenstein, and they acknowledge that, you know, the optical variability of one of the first quasars detected was one of its most noteworthy features. And here we are in 2021, and we still don't really understand what drives optical variability in AGN. And so, you know, the hope is that LSST is going to make great inroads into this and maybe solve the problems. But I'd like to take a step back and just sort of think more broadly about how we consider processes that lead to time series analysis, and particularly with AGN. So there's a great theorem that Wald, an economist, put forward in the late 30s, which sort of says that if you have any stationary process, you can essentially deconvolve it into a linear deterministic component and a stochastic component. Jeff Scargill wrote a series of papers in the 80s, and in the first one from 1981, he sort of rephrases this and sort of says that any stationary process, so this is a temporal process, a stationary process is a formal definition of something where the mean and the variance don't have any time dependency. So, and you can convert a non-stationary time series into a stationary time series by taking time differentials. So most of the stuff we can do can be considered stationary in some sense, but you can, if you detrend it, take away the deterministic part, then it can be represented as an autoregressive moving average process, one of these ARMA processes. Now, one of the questions to ask is that if you have any given time series and you do this decomposition, there will be different physical processes which contribute to that, either to potentially a deterministic dominance or a stochastic dominance. And so therefore, with different types of objects, different time series, we may be able to figure out, you know, which one is more chaotic, which one is more stochastic. This is certainly the case that they've done for the microquasar, GS 1915, and there are papers where they've demonstrated that it goes through periods of activity where it's got both going on. Well, what you can do is you can sort of consider this in, you know, some sort of parameter space where you maybe have deterministic to stochastic or degree of each of those on one axis, and then you have linear versus nonlinear on the other axis. And there are particular physical processes that we understand from a theoretical perspective that you can put in there. So we know that chaotic behavior is deterministic, but it's highly nonlinear. We know periodic behavior is deterministic and linear. When we know stochastic behavior, and these are the sort of things that we can model with an ARMA process, is linear, but stochastic. And then in the middle ground, there are some processes that we know that can be modeled with things like hidden Markov models or whatever, but there may be stuff as well. Now we can map different types of astrophysical variable sources into this parameter space as well. Most stars, most variable stars, go down into that periodic corner in the bottom left. They're deterministic and linear. They're either pulsating or eclipsing, or maybe they got star spots and rotating, something like that. X-ray binaries, probably more into the stochastic, but still fairly linear. Things like microquasars, as I said, seem to be fairly chaotic. They're probably up in the top left. And what we've been doing for the last 10, 15, 20 years is putting AGN into this linear stochastic bucket down at the bottom right. But the question is that really where it belongs? Are we thinking about the types of behavior or the types of model that are driving AGN variability in entirely the wrong way? So I said Scargill and Wald's theorem says that any process can be modeled as one of these ARMA models. And Brendan Kelly came around in 2009 and showed that, you know, the simplest ARMA model, the continuous autoregressive first order model, also known as the Ornstein-Uhlenbeck model, is a reasonable fit for AGN variability to describe it. But this assumes linearity, it assumes stationarity, it assumes reversibility, it assumes that there's no trend, that is just a constant mean. It's good, it's a good model to work with, A, because it gets around any irregular time sampling you have, which is a huge, huge plus, particularly for surveys like LSST. It also has a closed form solution, so it can be calculated analytically very quickly, and it's only a 2-parameter model, and you can attempt to ascribe those to physical process. And there's been a whole load of literature over the last decade or so showing that it works for some time series, but there have been deviations found. Actually, it suffers from biased parameter estimation. It can be degenerate, and it's really just the first of a whole series of models which introduce more complexity. So you go from Karma to Karima to Carfima. That's favored by Eric Feigelson, for example. And we just use a single process to describe an AGN, whereas there may be multiple autoregressive processes going on, and you can take that to the extreme limit. Have a look at the paper by Takata from 2018, where they consider an infinite OU mixture model. So it's a good descriptor, but it's probably not what we want to be doing. And so particularly as we are asking physical questions of our variability, we want our models to actually have something more than just purely descriptive power or to be a reasonable fit. First of all, we're asking, you know, we like to do AGN selection on the basis of variability in addition to color and other means. We're interested in identifying outliers based on the variability. And then there's a whole effort that's starting on trying to infer parameters from variability measures, from variability fits, whether those are characteristic timescales or black hole mass, accretion rate, disk aspect ratio, spin, magnetic field. There's some idea that the physical processes which are driving the variability and the physical parameters that those are dependent on are imprinted on the time series that we're going to be measuring and the variability that they're showing. And that may allow us to then determine what the physical model is and loop back to some understanding of what the actual processes close into the supermassive black hole are. But really what we want is we want somehow to map our input data, whether it's variability or alone or variability plus SED information plus imaging, to be able to recover these parameters, to do the inference, to do the regression. And this formulation is actually what is the fundamental of deep learning. And this thing called the universal approximation theorem, which sort of says that a neural network with a single hidden layer can actually represent any measurable function. So if you have input data and you have output data, no matter what the form of that is, deep learning promises that it will give you the mapping between the two if one exists as a Borel measurable mathematical function. We do this by constructing these layers, training the whole system. The other thing is that there are fundamental connections between neural networks and Gaussian processes. So if you don't like deep learning, but you do like statistics and you like Gaussian processes, they are essentially doing the same thing in some ways. But what's important is we're trying to figure out this, this universal function that maps the input to the output. One way of doing this is a thing called recurrent, is a thing called latent space models, which recurrent neural networks are an example of. And in this particular type of deep learning architecture, what you're learning is actually a lower dimensional representation in the so-called hidden layer of the input data. You train the overall model such that the input is the same as the output. But you've done that by encoding the data down to some lower representation and then decoding it back to your upper representation. And one of the reasons you might want to do this is that there's information encoded in the time series, or that the data that you're putting into your encoding network, which can be better extracted and better expressed in the lower dimensional latent layer. And so there's a whole branch of deep learning which is based around this premise, whatever. And this is very popular for recurrent or time sequence data, sequential data, more so than potentially for sort of image data or the sort of things that CNNs have been used for. And so what we did was my PhD student, Yutaro Tachibana, 2 years ago, decided to try and apply RNNs, which are the sort of simplest one of these latent space models in the deep learning sense, to a whole load of time series that from the Catalina survey. For those of you who don't know, Catalina is pretty much an all-sky survey, 10 years worth of data, single filter, but revisiting points on the sky about once every 10 to 15 days. So very similar to LSST in cadence, and also decadal baselines. And the data is all out there, goes to about 19/20th magnitude. You've probably got 500 million sources. Certainly there are a couple of million AGN just sitting there. And you're looking at about a 3% LSST in many ways there. So it's a great data set to start playing around with some of the sorts of algorithms on the type of cadence sampling you'll have with LSST and with those decadal baselines. So this is the paper that came out last year. We looked at 12,000 quasars. We separated them out so that we were actually only looking at so that we were excluding host emission, that we were only looking at AGN emission. One of the issues with RNN autoencoders, however, is that they don't handle a general issue with deep learning, is that the sort of traditional methods don't handle irregular time sampling. And so you have to put the delta t between successive time steps in as an additional parameter. We also tried to see if it made any difference if we put in the first and second time derivatives as well. It didn't really. But what we've got in here, so we have a typical light curve, which maybe has, we were looking at 500-day observations as just a good window in the intrinsic frame. So we're putting in maybe about 160 data points, delta t mag, and we feed the magnitude error in as another parameter. That goes through this particular network with a set of LSTM layers. In this case, we did try GRU layers as well. It doesn't really make a difference. Down to this hidden layer where we have 16 parameters. So we do reduce our set of 160 time measurements down to about 16 features, which the network has learned from the data. Of course, it then re-extracts that and gives you back the original data. And our loss function is also making use of the measurement error on this. So it constrains things very nicely. So this is the sort of recovery. This is the sort of data it was trained on. This is what Catalina light curves look like. And you can see, you know, the recovered light curves do a very good overall behavior basis. And if you compare this sort of recovery to what the Brandt random walk, the first order continuous autoregressive model shows, it's certainly equivalent or better. So already the RNN model is doing as good as the sort of most popular statistical model we might use for this modeling. But because of this hidden layer, we can also start asking about, well, is there any information actually in that representation? So we can take the hidden layer and we can run PCA on the 16 parameters, the 16 features that are used to represent the learned representation features. And what we see is that there is actually a sort of broad range of behaviors. There's a mapping here from this plot over to the sorts of things that the light curve would be encoding if for each of these data points. So you can see that there is some behavior where it is, you know, obviously a hump, obviously a dip, maybe it's a sort of flat behavior, depending. And there seem to be sort of probably 2 or 3 dominant areas one over here by O, one over here sort of G, and maybe a sort of peak around L, sort of showing the sort of dominant behaviors that we may be seeing. So at least in terms of morphology or in terms of shape parameters, this seems to be extracting something and telling us something about the sorts of things we may be seeing in AGN light curves. The question, however, is there any physical information? I mean, this is purely morphological information in terms of shapes, but can we do anything more with this? And so what we did was we took our 16 features and then we reduced it down to a single feature, just a single parameter for the sake of easy computation. And then compared that against other typical features that are extracted from time series, particularly things like tau and sigma if you were fitting a damped random walk model, and saw how those correlated or partially correlated with things that we knew about, like black hole mass with redshift, extinction magnitude. And what we found is that the features that we've learned, that the compressed feature that we learned from the time series that the deep learning is giving us, does indeed seem to correlate with physical parameters. So the deep learning is extracting information that's encoded in the time series. And it's not just morphological. And it's doing it as well as the standard statistical models. A more interesting
thing. You got about 3 minutes.
Yeah, thanks, Gordon. A more interesting thing that we found was that if we actually flipped our time series and put it through the same thing, both in terms of time and in terms of magnitude, we found that actually there's a time asymmetry in the sense that our time inverted AGN have a different prediction recovery, different modeling accuracy, which is not shown by the damped random walk model. And what this is telling us is that there is an actual asymmetry, a temporal asymmetry in AGN time series that this particular way of modeling is capturing that the more standard statistical models don't. In fact, the damped random walk model assumes time reversibility, as I said. So there are problems that with what we are currently doing, and the things that we need to be feeding into what we're doing for things, for modeling, simulating. The other thing is that the magnitude of the asymmetry seems to decrease as luminosity or black hole mass increases. So there's a physical effect on this. There's a physical dependence on this effect that we're seeing. But this may be consistent with some models of the accretion disk and what's going on. We're now moving into ZTF, applying this sort of thing. This is a 10% LSST survey. The cadence is much better, and we're already at about 1,000 data points, and you get colors as well. So some combination of the two is really good. The other big change is that there are now continuous time deep learning models where you're mapping your data, even if it's a regularly sampled, onto some continuous hidden state, which then can be described and evolved by, for example, differential equations. And I know Ashley maybe, or Jean Cohn may be talking about that later this week. So these are things like neural ordinary differential equations, neural conditional control differential equations, neural stochastic differential equations, continuous time RNNs, continuous time echostate networks, and liquid time constant networks. There are a number of these going on. It's an active development. So this problem of having the irregular time sampling, which has always been one of the big problems with our time series analysis, has gone away or is going away as we move into these more sophisticated models, which all go back to this latent space representation. So the lessons for AGN variability in the LSST era. A lot of work has been done on Kepler test AGN light curves, but they're very detailed and they're single source. LSST data is actually much closer to some combination of Catalina and ZTF in terms of coverage, color, cadence. In LSST, studies of extreme behavior are going to be population-based rather than single source dominated. And so we need to be able to handle large components of these in easy ways. Follow-up is also a very limited option for most of our sources. So getting the temporal modeling and the temporal analysis is paramount. Getting that right is paramount. However, there's a limit to the information that can be extracted because we don't have Kepler test type light curves, we have CRTS ZTF type light curves. And so we really need to have a deep understanding of what the fundamental assumptions are when we're applying these techniques. And if possible, use techniques that make very limited assumptions. Deep learning, I think, promises to be the best tool for doing that, particularly as it can handle nonlinear phenomenology without adding extra features into, as you may with a more conventional statistical model. And there are new MDL developments with continuous time that I briefly mentioned. Also things like uncertainty quantification and interpretability, which I think hold much promise to study the baddest and the weirdest of objects that are AGN. And I'll stop there. Thanks.
Great, thank you, Matthew. All right, we have time for a number of questions before we take a break. Mara Salvato can get started.
I think it was up from before.
Okay. Questions? Colin Burke.
Hi, thanks. I'm curious, does your model have any requirements on the quality of the light curve in order to get accurate results, such as the length of the light curve, or does it do better than the damped random walk modeling?
It does. I mean, it does better than the damped random walk. If you try and apply the damped random walk to infer the same things or whatever, you don't see it. But that's because the damped random walk already has made a number of fundamental assumptions, or you've made a number of fundamental assumptions about the type of process that you're investigating by applying that particular statistical model.
Cool, thanks.
Sebastian Hennig.
Okay, thanks, Matthew. It was really nice talk. I really liked it. I have a question. When you do when you showed the data versus your recovered light curves, it looked like the high frequency part wasn't quite well reproduced. Was it just kind of an optical illusion, if you want, because of the error bars, or did you actually try to compare the power spectra or structure functions with what you recovered?
Right. So there are a couple of things I would say there. First of all, again, with these assumptions, power spectrum and structure function are essentially a second order statistic, and they don't give you any handle on nonlinearity in your time series. So you need to be, we really should be moving away from those, particularly if we believe that we have nonlinear processes which are driving our variability. You can easily construct a power spectrum for two different time series processes that look the same. In terms of the actual the data showed, it's unclear whether the short-term variability that is being shown is actually real, or whether it's inherent in measurement area and stuff like that. So one of the things I have with the damped random walk is, you know, that when you fit damped random, when you fit at least a CAR1 model, you sometimes are picking up the intrinsic just night-to-night variations. And so therefore you avoid the very shortest timescales. So it's a little hard still on these cadences, I think, to understand what the interpretability, the variability we're saying. I think the exercise that needs to be done is to actually take Kepler or test light curves and to downsample them to the cadence that we see with these with the ground-based surveys, and then see what the range of variability we're seeing at that particular timescale perspective is.
Okay, thanks. I mean, that's just one additional comment to that. I mean, it's true that you say the structure function and the power spectra are not unique. However, they're exactly good to find high frequency features or something like that, or see if this is kind of just measurement errors, or if it is intrinsic to the data, right? I mean, this was the purpose why I thought if you'd essentially just took structure function or power spectra of your reproduced light curves.
Yeah, but we know, I mean, we know with AGN that you can't get information. I mean, the problem with the structure function, as you know, is that once you get below about 5 days, the photometric error becomes the dominant term, and then you have to do, you know, machinations to work around that.
Yeah,
and it's
yeah,
not
exactly.
clear what the best approach for doing that is. So yeah.
Okay, good.
And last question from Paul Sanchez.
Hi, Matthew. Thanks for this great talk. So one question actually related with what Sebastian asking. So do you have any ideas how to more properly fit short-term variability with this kind of models? Because I'm, you know, trying to use the same techniques, but the problem we're facing is trying to model the short-term variability, for instance, from low luminosity AGNs or blazars. Any ideas about how to deal with this?
Not offhand. I mean, it is. I think we will do somewhat better with LSST because of the better photometric accuracy. It's not clear to me yet how much better we will do. However, because it has a longer cadence between the visits. And so I think there is, as I was saying to Sebastian, I think there's modeling that can be done taking the space-based AGN light curves that we have, and you know, sampling those down to some of the ground-based, and then to LSST and see what that would look like. And you know, the other thing is, once you start putting constraints into model the short-term variability, you are then putting again, you're making a particular assumption about what might be going on with what you're seeing, rather than trying to see what is real signal and or hoping to be able to decompose between a real signal and systematic effect from sampling or something like that. So I think there's work to be done there. I think it's an interesting area to work, but I'm not certain I have any clear solutions in mind at the moment.
Okay, thanks.
Okay, great. Thanks, Matthew, and also Matthew Temple. The earlier talk. So we are going to let's take a 15-minute break to 1:30 Eastern, 13:30 Eastern. And then Weixiang Yu is going to give the last talk of the day, and then we're going to follow straight into discussion from there. Okay, so we'll break until 1:30 Eastern. Yeah, I think there's a few we can identify. Roberto had mentioned something about posting things in Slack. Roberto, do you have a suggestion for what channel to use for that, if people do that?
Yeah, sure. No, I was thinking people can also post them in the AGNSC channel directly if there's any questions. We don't have a dedicated channel for this, but that way, in case you lose track of or anybody loses the chat window for some reason, it's we can have it all there. We can all see it there.
Okay. Okay, Weixiang, why don't you go ahead and get started? So Weixiang Yu from Drexel University is going to talk about the AGN data challenge that Niel mentioned earlier, and relate that to some variability metrics that he is working on. Why don't you go ahead?
Okay. So you hear me okay?
Yes.
Yes.
Okay. All right. Thank you. So I would like to talk about the data challenge and some associated variability science that we can do with it that we just announced last Friday. Before I start, I'd like to thank those who have contributed to this project, especially Veronique, Amanda, Qingling, Repo, Matthew Temple, Vega, Jingyi, all the judges, and many others. So, okay. So there are three goals that we aim to achieve for this project. One is parameterization of AGN light curves. AGN selection, AGN photo Z estimation. We have received broad support from within and outside the AGN collaboration, and thank all for your support. So together with the data challenge, we released an exploratory data set. We built this data set using sources from two main survey fields. One is the Stripe 82, another one is the XMM LSS area. The Stripe 82 is the main testbed for variability related projects. And we have extended the initial SDSS Stripe 82 region to a broader area for maximizing overlap with HSC and DES coverage, where you can see in the top footprint figure that is shown in the blue boundaries, and the area shaded in green is the initial SDSS Stripe 82 area. And the XMM LSS area is served as testbed for more of a true stable because it has much deeper and extensive multi-wavelength coverage. So for the data sets, we included roughly 500,000 sources in three main categories or main classes: stars, galaxies, and QSO/AGNs. For the objects that are located within the initial SDSS Stripe 82 region, we have collected light curves for about 220,000 sources. So for all the sources, let's start with the Stripe 82. For all the sources in the Stripe 82 data sets, we have cross-matched them to different multi-wavelength surveys ranging from UV to radio. We also get the astrometry, more specifically performation and parallax measurements from Gaia and NSC. For those who are not familiar with NSC, that is the IR Lab source catalog. For the time domain data, they both just come from the SDSS Stripe 82, and spectroscopy, if they're available, will match to the SDSS spectrum database. For the XMM LSS region, we add in deep X-ray data from XMM served. This area doesn't have time domain data, unfortunately. And for the optical to IR, we use much deeper data from HSC, Vista, and Spacer Deep Geo. Here are just some statistics for your reference. I will link my talk in the chat later so that you can have it whenever you need it. And here is some matching statistics between the different multi-wavelength surveys and the different classes of sources in the data set. Okay, so we can't just dump all the data to you. So we put it try our best to put in the format that whatever LSST you're going to use for the data release. So basically, there are three main tables and one multi-wavelength table that's just presented at this. The first main table is called the object table. You can think of it as a table of unique, real astronomical sources or objects. I should use object in the LSST nomenclature. We used catalog from deeper surveys to emulate this table. That include like photometry, color, astrometry, time domain data. Time domain in terms of extracted light curve features. That's also part of the LSST data release. We included both spectroscopic and photometric redshift, but however, based on the current data model, only photometric redshift are going to be available. Also added classes just for the purpose of data challenge. It doesn't seem like the information will be included in the data release either. We're adding flags, just some general useful flags concerning the quantity of other measurements in the data. For the source table, is more like measurements made on single epoch images. We added those includes like RN deck, flux morphology. Again, filter, I underline it because based on the current model, data model. It won't be included, but you can cross-match with other tables to get it. But we just include it for easy access. The forest source table is more like a place that you will go to get light curves. LSST will use force photometry to generate light curves, but however, we don't have the resources to do that. So we just cross-match with our source locations with the SDSS Variability catalog database to get whatever we can. And we emulated the different flux. For more information how that was done, you can get it from the GitHub that I will link later. I'll also edit a filter. And like I said, all the information are actually hosted on GitHub. You can get started from there. And the data sets are actually hosted on site server. It's a great environment for you to get started to play with the data set. Also, site server uses the Jupyter Lab, the interface, which will be quite similar to what you would see whenever the LSST comes online, based on the current design of the LSST science platform. Okay, next I'm going to do a quick, walkthrough of this, the GitHub repo and the site server. Yeah. Okay, so here you see my share screen.
Yes.
Okay, good. Yeah, I was switching stuff. So this is the GitHub repo, which is actually linked in the announcement from last Friday. It provides a lot of instruction information. Most importantly, you need to set up an account on site server and fill out this Google form so we can add you to the group, so you can get access to the exploratory data set. And then we'll send you an invitation, and on the left is what you're going to see from your own, from your side. Let me try to. Okay, never mind. So you're going to go to the groups there, and then you would see a invitation, sent from Drexel LSST group. Are you going to do it? Just accept the invitation, and then you go to compute. What's more important is you need to create a container so that you set up a computing environment to interact with the data. So let's say just do DC test, and you can just select site server essential. Once you are accepting invitation, you will see the share volume from YWX, this username. That's where all the data are hosted. If you don't click this checkbox, you wouldn't see the data shared. This will take a second to spin up the container, and then you just click on it. It will link to you a that's called the classic Jupyter Notebook interface, but they have a link. You can go to the Jupyter Lab interface. So I wouldn't go through the downloading like a Git clone process because it takes some time. I have already done it. So let's go to the right of the screen. Basically, when you come in, that's what you're going to see. You have on the left is a sidebar to show you how to navigate through the file system, and you can just go to persistent is where you store all your long-term stuff, right? And I already downloaded or cloned the data challenge in repo, so I just go in. We have a couple of folders. Doc describes how we build the table, like how the columns were converted from the column, the catalog data. And there's a couple get started notebooks that we put together to help you, to get on board. Let's just see one. I wouldn't run them because it do take a few seconds, but you can basically, once you clone this GitHub repo, you can see all the information, and you can just feel free to hit run, and that will show all the information that was there. And the forest source table is for loading in the light curves. This is an intended error. You can get more information from the GitHub repo. to see why that's the case. So you can basically, plot whatever light curves for the objects that has that in the from the object table. Okay. Let me just switch gears. That's all I have for the walkthrough. Okay. And come back to the presentation. So some future works related to the data challenge is we need more class labels for the variable stars. We need more, apparently we need more light curves, in particular like forced light curves. Personally, I haven't do a lot of investigation in the difference between forced light curve and cross match light curve, but may play a major role for fainter sources. A light curve for XMM LSS sources with matching depth, that will be really critical for us to get a real taste of how doing either selection or photography using both variability data and color data and other data at the same time, right? And simulated data and augmented data, they're all good to really enrich this data set. One thing I want to mention is this is really unfunded effort. Yeah, we got fund for prizes, but not for putting together these data sets. And we really need more people to get working on this so that we can get a truly ready training data sets for agent selection and agent photo Z estimation, targeting the LSC data set. This is only a start, and a ton of work needs to be done in that regard.
Wait, John, can you switch back to full screen view?
Oh, I'm not full screen?
You're now in presenter view after the demo.
Sorry. Okay. Okay, now you see the full screen?
Yes, much better.
Okay, sorry, my bad. Too many windows open. Yeah. So there's a lot of work that need and should be done. And I want to call out for participation from my junior fellows, and really only with your contributions and support and giving our feedback, we can make this data set much richer and better, so we can get ready for LS data whenever it comes online. And on the other hand, I mean, we have a lot of participation award. If a participation award can give you, a Mac Mini, maybe not a full one, but why not, right? Okay. Now I want to switch gear to talk about a variability matrix. It makes no sense to not talk about a variability matrix given that
about 3 minutes.
Oh, shit. Okay. So there's two categories of variability metrics. The first is periodic features. They're mostly taken from the research et al. 2011. And non-periodic features, on top of that, we add in camera features, and just some figures showing that we can actually do selection, or the utilities of using variability features to do selection. For camera 1.0, I'm just showing that the distribution of them. I just want to point out there are actually a lot of bad fits, given that the limited temporal sampling in the photometric uncertainties. After removing the junks, we can see it has some utilities to do selection. And more I want to emphasize, probably not having a lot of time left, is Karma 2.1. Matthew Graham has given a good introduction to the GRW and Karma, but most people may not be too familiar with Karma 2.1. It is formally defined as a solution to the stochastic differential equation shown on the top, where X is the flux levels. It resembles the form of a driven damp harmonic oscillator. So that's why I call it DHO. A more visual representation of DHO is through the power spectrum. There's a lot of utilities of doing DHO. Hopefully I can go through them all next. Here is the first selection. You can see that the green part represents the distribution of quasars. I want to point out that those are the alien thing effects kicks in at 1 day, half a day, and other harmonic time scales. This is using SDSS data. Maybe for LSST, it won't be an issue. We could possibly, using the issue to do a very complete and clean selection of AGNs, meaning that we can remove a lot of the junk. And actually, what DHO really offers is better modeling of the light curves. So the first thing we may wonder is how would the light curves look like with light points from different part of a distribution of quasars in the DHO space, right? I did that, so it's like a couple points, and see how the similar light curve looks like. So from this branch, you will see some light curves that are smoother and having more long time scale variability. And from this branch, as you go to the top right, you see more and more short-term, short time scale variability. And more like resembles the morphology of DRW light curves. And then we could ask, how could we connect the morphology of the light curves to astrophysics or physical properties of AGNs? One way we can do that is think about this in terms of different corona geometry, given the lately model, right? The more smooth light curve could represent more light from the disk, where the X-ray is blocked from directly illuminating disk, and the more short time scale or short-term variability could really just reflect more X-ray variability, where the X-ray corona can directly illuminate the disk. In addition to that, DHO has some potential utility to do binary supermassive searches, because the model itself is flexible enough to allow quasi-periodical signals to be modeled. And this left plot showing a classification or some framework sent by Moreno 2019 to characterize quasi-periodic signals, which is basically using this parameter, which is defined as the rate. We may wonder how would that, how would the real data look like, right, in terms of this classification framework. Again, I just showing the distribution of QSOs in the DHO space, all the lines showing corresponding different values of this damping ratio. And basically, based on the Moreno framework, those points could potentially be having quasi-periodic features. So I did the same as what I was done earlier, to simulate data taken from this part of the parameter space and see how it looks. And yeah, we got some quasi-periodic signals there. The last slide is just showing that the point I'm trying to make is there's a lot of utilities of doing DHO modeling. Is way beyond selection. Also, given the framework we set, the connections between the morphology of the light curves and the district geometry, we can use them as a way to select interesting objects for spectroscopic follow-ups, and also the different geometry could correspond to different emission line features. I mean, when the LSST come online, we can't do spectroscopy for all of them, but they give us a way to select interesting objects so we can do a deeper and further investigations in terms of physics. And all I have. Thank you.
Great, thanks, Weixiang. We have time for some questions. There's like 4 questions in the chat and on Slack, so why don't I read those out, and then if there's maybe one more question live, we can get to those. Robert Nakuda asked if the data will be available in the table access protocol.
Yes, the fits and all the light curves are available through the table.
I think he might have been asking something more specific, but maybe we can talk about that offline.
Yeah.
And then Marla Salvato wanted to know if extinctions are available and if the X-ray data in Stripe 82 would be useful.
The extinction value are not included for this particular data challenge, but we can certainly talk about how we may able to share that. And yes, I think X-ray data will be useful. I mean, in the Stripe 82 area will be useful. We just haven't got time to incorporate that, but it will be good to have some help in that regard.
Yeah, and I'll follow up and just say we're aware of the existence of X-ray data in Stripe 82. The issue is, it doesn't cover anywhere near the full area, so it does sort of make for non-uniformity, but we could certainly talk about including. And then Paula Sanchez asked if variability features are corrected by redshift and if variable stars are included in the star class.
So for the first question, for the plot that I showed you, yes, they were corrected for, those, I think they were corrected for redshift, but it doesn't really make a huge difference given that they're all in the log scale. And the alpha 1, alpha 2 parameters are not directly related. Well, it depends on which one, are not linearly scale with time scale. And for the second, yes, the variable stars are included in the star class. That's right.
And I think Franz had a follow-up before this one more question. Are variable sources cut at some significance? That is, they have to be variable by some amount.
We didn't cut based on any, well, so the variable stars were collected from the IPSICH 2007 variable catalog in the Stripe 82 area. We cut it based on our index because due to the, there's one region that's not enough, SDSS spectroscopic coverage, so we just removed those so that to reduce the contamination. And whatever other costs that were applied was all from IPSICH 27 variable catalog. I think that was based on G and R band magnitude and some other criteria. But I can share with that information if interested.
And the last question, Luke Kelly wants to know what's the cadence of the data? That is it just the source cadence, or is it matched to LSST?
No, the cadence is not matched to LSST. It's just a source cadence from the SDSS Stripe 82.
Okay, so we should move on to discussion, but if there's any last question, feel free to shout one out.
I can ask a question, which is, this is all done at the catalog level, and this brings up issues of different PSFs and different surveys and how one actually does the matching given the different resolutions and blending issues like that. At the depth of STSS, I think we're probably mostly okay, but at LSST depths, this is likely to be a significant issue, and maybe something that's worthy of discussion as we go forward.
Yeah, I think I totally agree. There's a lot to explore, in both the light curve aspect and the the photometry aspect.
Paula Sanchez, a last question?
Yes, thanks. So how do you define the galaxy sample? Is there any possibility that some AGNs can be like Seyfert's present in that sample?
Yeah, that's a good question. That wasn't like, it is possible. I can tell you that it could be some match that something is both an AGN and a galaxy. We don't have a specific class for those because it takes some, expertise that is beyond my my level to really classify those, or some extra work that needs to be done to do that, I think.
Okay, great. So we should move on to discussion. Feel free to post things in the chat or on Slack that you would like us to discuss. I can identify sort of two things, unless somebody wants to start with other things. One is just in terms of the variability following up from what Matthew Graham and Weixiang were talking about, certainly, what is it that we can get out of sort of more complicated light curve parametrizations than dampen and walk, and how can we, connect that to quasar physics? I think there's a lot of hope there. And then the other thing is that, sort of following up on Michael Strauss's point, which actually connects host galaxies and variability together, is, that in fact, the light curves in the data model, at least last I understood it, were going to be differential light curves, right? So that is, we wouldn't actually have light curves of the whole system necessarily, but after, sort of running difference imaging. And then, we sort of lose the DC offset information, or at least in sort of exactly the way that you might otherwise expect.
Well, and it's very recoverable, of course.
What's that?
It is recoverable. I mean, you can get that DC back if you want, because
yes, but I posted something on community like 3 or 4 years ago, pointing out that there wasn't an exact match, and there was sort of some head scratching about how that would actually work, right? That is, the type of photometry in the difference imaging is not the same as the overall photometry.
Yeah, that's true.
And then I don't have a specific question or a topic for hosts, but I'm sure that there are things that people would like to discuss there. Although I do think we have lost John Silverman, but that doesn't mean that we can't get him to participate in the offline. Okay, so with that in mind, is there anything that people want to call out? I see a number of things on the chat, and if somebody wants to take one of those things that I talked about and run with it, or suggest something else, by all means, go ahead. Otherwise, since Maurizio and I, have the same issue, and Michael just brought it up, maybe we can talk about that for a few minutes.
Gordon, just to pick up on your comment, I have a student that was working on the difference analysis, although not on some precursor VST data. And it is challenging to get the same thing from the force photometry and the difference imaging. There are more tricky problems than one expects. And I expect these to get worse with LSST. So the idea now was to try to test it on the LSST pipeline, because it's potentially better to go deeper to retrieve faint AGN, but as you said, you don't get exactly the same match, and you have to understand the biases that you're introducing, mostly data driven or software driven due to the data reduction. And I think that the difference imaging is so far has been thought for doing supernova and transients. So nobody has really deeply thought about what's the effect in the case of AGN. I think everybody assumes that it will be only force photometry, but it would be a pity not to use the full potential of the pipeline.
Yeah, so I think the main thing that I would emphasize here is just that at the very least, it would be useful for people to understand that the light curves that they think they are going to get may not be the light curves that they will actually get, and that there's some utility to us thinking about and talking about that ahead of time. I don't know who's on from the DM group. Sophie Reed, certainly. I don't see Yusra, but if anybody that sort of has expert knowledge of this, wants to give a short explanation, that might be useful.
I'm happy to help where I can, but I missed some of that because I got distracted by a cat. So if you could just rephrase the question for me, then I can try and answer.
So the issue is essentially that the light curves, as I understand it, are going to be from difference imaging, right? And so it's non-trivial to sort of match that to the force photometry so that you have not only the changes with time, but the overall, flux level of your source, right? And so people might be expecting to have the light curves, from say the forced photometry directly.
So if I think, as I understand, this becomes ambiguous, for example, with a quasar with a host galaxy, where the difference imaging will be a point source, and the undifferenced image is convolved with the host galaxy, and so you don't, or has the host galaxy superposed. So it's the true 0 point of the light curve is ill-defined without a PSF host galaxy decomposition of some sort. Am I saying that right?
You have to fit the reference image that was used for the difference imaging to make that separation.
As opposed to any other image. I mean, the reference image is the thing that you've subtracted away. So that does define your 0 point. But you still have that host galaxy contamination. So I don't know if there is a right thing to do. That is whether we should be telling the DM team, you should be doing this rather than that to make this more easier to interpret.
Well, and keep in mind that the reference image can change. So it will probably change. So maybe we have to have at least one reduction in which there is only one reference. So as time goes by, these things doesn't change continuously.
I guess another point is, of course, you don't know what's underlying the nucleus, right? There's a star cluster there. There's galaxy emission. So you're never going to have a precise estimate of what's actually from the AGN and what's not.
I mean, that's part of the modeling challenge. I mean, there's science in there. You model the light curve as AGN plus non-varying stuff plus whatever you see to be varying, as it were, something like that.
But there's a component of the AGN which is non-varying as well.
Right, right.
Sorry, one comment. So in the data list, you will find forced photometry over the science and the difference images. Just a comment.
Yeah, so I guess that's another issue, right? Is that there's a difference between what we're going to get in the alerts and in the data releases, I think what Paula just said is, I think you're arguing that we will have the sort of true light curves in the data releases, but is that actually true? Does somebody know that?
I think my understanding is that for the annual data releases, they will all be, I think, this is something to check, that they will all be reduced with a single subtraction template so that there'll be no discontinuities. But that will not be true alert by alert. As part of, I think, as my understanding, that is part of the reason that all the alerts will sort of be reprocessed in the annual data releases.
So you're saying that there will always be subtracted images that will get information?
I believe that is correct, but I'm saying that with modest confidence, not 100% confidence.
I think that's something that we might want to look into.
If you go to the data products document in section 4.2.4, you will see that it's for both, for the data releases. In the alert stream, it's only for difference images.
For LSST?
Yes.
All right.
Even if you don't know the separation between the host galaxy and the AGN, it's useful to have some measure of what the flux in the reference image was, so that you know where the 0 point of that light curve might be. So I think some analysis of the reference image is necessary for each object that's reported.
And I mentioned that with Vincenzo Petrecca, my student, we also realized that we were getting the difference images for sources that were detected variable. And as the AGN collaboration, we may want also difference images for objects that are not detected variable, because maybe we want to use that to push our detection limits. So that's another issue.
Yeah, and I think this is actually something that Matthew Graham has brought up in terms of like things that are variable not being identified as variable because they're not variable enough.
It's the opposite problem. It's galaxies are identified as variable even though they're not.
Because
seeing and noise
Yeah.
fluctuations and the error is not being estimated correctly.
Yeah, but Franz, that's for the force photometry. But if you see the alert stream, that's not an issue. In the alert stream, the problem is that you never get alerts.
Talking about the alert stream. We're talking about large, AGN variability embedded in host galaxies.
Oh, yeah.
But it also depends on the time scale. Like it might not trigger 5 sigma in a few days, but over a month, something may increase by a lot, but it won't make the 5 sigma trigger even in ZTF. I thought that's what he was saying.
Or it makes the 5 sigma detect, it makes the 5 sigma trigger, but only 300 days into the variable process.
Isn't it true that when an object is defined to be variable, there's at least a mechanism by which you can go back and get the light curve, even if individual points did not go above 5 sigma?
Data release.
I think that happens at the data release. I don't know if that, I don't think that happens routinely at the alert stage because it would just be too many objects.
There are Rubin or CTF? Or both?
I'm talking about Rubin. I do not know about CTF.
Okay, in Rubin, you will have for a given alert, you will have force photometry for 1 year before the alert. So whenever you have an alert, they will provide force photometry 1 year in advance.
Okay.
So you can.
But I don't believe sorry, Paula, but I don't believe you can get force photometry of any random position on the sky in Rubin.
Well, yeah, that's what they claim in the documentation.
I'm a little bit confused on how much of that is available on the 60-second timescale, which sounds like a lot of processing, versus something.
I think that's the night after. That's I think the force photometry, if it's newly generated, it's done the night after.
No, it's in the alert package, isn't it?
Well, that's
only if it's not new. If it's been detected before, then they'll include it with the next alert release. But if it's the first time it's been done, it will be they'll wait until the daytime to do all the force photometry. It won't be done in 60 seconds.
Okay.
Yeah, what Ashley saying in the chat is true. So it's for 24 hours for the force photometry, but features will be available in the alert package.
So can I make a suggestion? I don't want to get bogged down in sort of one topic, so we can discuss a lot. The TVS Science Collaboration, who we drew the AGN Science Collaboration Charter from, has this concept of a task force, and it sounds to me like we might, need 1 or 2 task forces here. One is just people understanding and making sure the entire science collaboration understands, what sources will be identified as variable both for the alerts and in the data releases, and then exactly what photometry we will have for light curves again in terms of the alerts and then the data releases.
So I was just talking to Yusra, who sends her apologies, but she's currently in another meeting, because she can probably answer many of these questions and put plans into action better than I can, or maybe anyone else can. If people wanted to get in contact with her or arrange like a little time when she's not in a conflicting meeting to chat with her, that could work.
Well, perhaps if she's able to come, we have discussions like this tomorrow afternoon as well, do we not? So maybe if Yusra is able to attend that might be very useful.
Okay, shall I suggest to her then tomorrow afternoon could be a time for people to ask these questions again to somebody with the knowledge and power to do something about them?
It sounds
Yeah, that'd
sensible
be
to
great.
me. Yeah.
Okay, I'll pass that along.
Okay, so I mean, the other thing that came to mind that came up is certainly the issue of essentially quasar variability and physics, right? So I guess the way I would look at that is, can we say something about, for example, L/Ludington for individual objects, or at least in the ensemble average, without actually having a spectrum, from the variability? I think the answer is probably yes, and there's a little bit of homework that we all need to do on that. I just want to give Matthew Graham and Weixiang and anybody else an opportunity to sort of follow up on that.
So the question is whether it's possible to infer from the variability.
Yeah, essentially, right? So I guess, the model that I'm thinking of is sort of the one that Weixiang showed, right? So in a sense that if your X-ray corona is impinging upon the disk, then that is going to enable the optical UV light curve to have sort of higher frequency variability than if the X-ray corona is not impinging on the disk, right? So you might expect that means that the variability would be significantly different as a function of L/Ludington.
Yeah, and I think what's also going to be important there is color variability. Because you're going to be probing different parts of the disk, and so there'll be a different temporal response as things work through the disk. So this is a sort of thing we haven't really thought about much yet, but I think it's going to be it's an important observable of whatever physical processes are going on underneath.
I got a question. Isn't that also dependent on other properties like the size of the disk, the black hole mass, and etc. for determining how that will correlate with the color variability, and that will call to, I think, more. We got a lot of spectrum from EBOS, but then they're lacking some measurements on the properties of the AGNs or quasars based on those spectra. The thing that I'm currently using is still like Shin 2011 for doing some of the explorations. Given that the DHO fitting are more prone to low sampling or high photometric errors, I think that would be a lot useful to have larger samples to explore whether we can see more of the correlations or not.
Yeah, I think that's right. I mean, I think one thing that'll also help this is when DESI starts releasing results. Once we start having, data sets where we have photometric plus spectroscopic monitoring of AGN, that's going to give us the training sets to set up the necessary models that we can apply whole scale to larger sets.
Yeah, I think for more photometric data or light curves, currently we're more limited to the SDSS REP82. To the depths in terms of taps and photometric errors. Other surveys will provide a lot better cadence, but like the depths, probably not as comparable to SDSS.
No, but if you're thinking about what you ultimately want is something that you can apply whole scale to a large photometric data set. So you want, and we're talking about something machine learning or deep learning. You're going to have a training set which is going to be made up of a small set where you do have the information.
Right. Yeah.
But the ultimate thing you're going to be applying it to is just photometric data. But the hope is that your model will be sufficiently powerful enough that it can do the inference in the absence of spectroscopic, or maybe just one reference spectrum or something for some subset.
Okay.
So, I mean, related to that, I posted in the chat, you know, comment about Kepler and K2 and TESS.
Yeah.
And, you know, there was a point in time where I was extremely excited about Kepler, you know, given that it had 30-minute cadence. And we are, I think, like 4 days short of having a paper withdrawn from the journal if we don't respond to the referee. But it actually is on the archive. But I mean, basically, I think we can show that the Kepler light curves are all junk, at least, you know, fainter than you know, as faint as we need, right? So sort of 16th to 18th magnitude objects. They're all related to temperature-dependent focus issues that I think we can show quite strongly. And then the problem with TESS is basically the same. It's sort of limited to 16th magnitude, right? So, so we can get really great light curves for, you know, handfuls of AGNs and quasars at 16th magnitude, but not perhaps what we, you know, really wanted or hoped for.
No, but again, it's the, you know, it's the inference story, right? That if we can understand what the local bright population is doing, that maybe gives us some handle on what we can infer about the broader population. I mean, the alternative, as I said in the chat, is the deep drilling fields. But we need very.
Yeah, I mean, the deep drilling fields are clearly giving us what we want, right? The question is, you know, do we have any data that we can use to sort of predict what we're likely to see in the deep drilling fields and know how to then deal with it?
Yeah. I mean, we've done a couple of deep drilling fields in ZTF, but you know, you get nobbled by the photometric accuracy. And I think that the thing with the deep drilling fields is to get the information on the short-term variability for AGN, there's going to have to be some special work done to really reduce down the photometric errors above and beyond what might be in the actual catalog.
Can you give us numbers? How precise do you need, and what are you worried about that the normal catalog will not?
Well, it's the structure. I mean, it goes back to the point that Sebastian was making about the structure function.
Mm-hmm.
That with regular AGN observation, you know, when you construct the structure function normally, the photometric error kicks in, or the amplitude of the photometric error is at about the scale of variability, intrinsic variability from the AGN that you would expect to see on the sort of 3 to 5 day time scale.
Uh-huh.
So if you want to have some handle of what the variability is less than that, you have to try and estimate what the systematic error is, or try and improve your precision with, you know, differential photometry or something like that.
Well, it is different. Well, let's see. I mean, again, it's difference imaging that is doing the photometry.
Yes, but I mean different photometry in the sense that you would maybe forward model, or you do scene modeling of the neighboring stars as well, and assume that they're all constant, and then get a tighter handle on what your precision is, not just on the single object.
Right.
That's what difference imaging does.
Not exactly,
yes,
but
it does.
It can be. I mean, those kind of exercises can be done after the fact at the catalog level.
Yes,
and this might be another thing to ask Yusra when she joins us tomorrow. She will have an opinion on this, a more learned opinion than I ever will.
And Matthew, let me ask and follow up to that. Would you want any particular changes, or do you have any suggestions as to how the deep drilling field observations themselves should be done to optimize this?
Not offhand, because I think it's only something that's really only occurred to me this morning.
Okay, but well, if you have a chance to think about
yeah,
that,
yeah,
it'd be a valuable thing. That way the observations. I mean, unfortunately, it may be a little bit late to even get our inputs in because of the cadence notes were due back in April. But
yeah,
hopefully,
no, I mean,
if there is some highly important thing, Željko, for example, is keen on AGN variability, and I think he would be receptive at least to listening to us.
Yeah, my suspicion is that it can actually be fixed post observation by doing more detailed data analysis, and that's certainly, within ZTF, we have a group who are trying to improve on our overall photometric accuracy by doing a much better job of PSF modeling and trying to identify very low level systematics and things like that, which may pay great dividends. But in terms of just the basic observations, there was nothing really we could have changed to produce the data. So I suspect that the same is true probably for Rubin, that the cadence or whatever is going to be fine. There's nothing you're going to do about the observations, but it's the detailed modeling of the environment, of the what the atmosphere is doing, and maybe other things like that, which can give you potentially exquisite PSFs or whatever, pixel level PSFs.
I imagine one issue that will come up with the deep drilling fields is exactly how the dithering happens. And I think that's what, and I know when this conversation has come up with people in the project, working DM and thinking about commissioning and so on, basically they said, let's see what the camera performance actually is before we try to second guess, because it will really depend on things like scattered light and ghosts and all kinds of nasty things like that.
Yeah. I agree with that statement entirely, Michael. You'll be surprised what cameras can do.
I think that's right.
Okay, so other comments on this thread?
I was just wondering about the simultaneity of filters, because color information is important. Like in ZTF, sometimes they're spread by several days or more that can cause problems, and LSST might end up the same way.
Well, are you interested, Paulo, for the deep drilling fields or for just in general?
In general, but in the deep drilling fields, I thought you got them within a day, but is that settled?
Yeah, we asked. Well, yeah, nothing is settled, but I believe we did ask for them to be done, in rapid sequence to the extent that's possible. So.
Yep. Okay.
Yep. Now I remember there was debate on this last year as to maybe that wasn't the best choice. Maybe it's better to actually have a little bit of difference, and then you can get better model constraints. But that's what we asked for.
In general, they're going to be the current plan, I think, is to carry 2 filters per night, separated by a half hour to an hour, typically.
For wide, fast, deep, yeah.
And for deep drilling, the deep drilling will probably even have more filters because just to fit in everything.
That's what we asked for. Yeah, we asked for it to cycle through all available filters every time the observations are done. Yeah.
I don't know if all available filters is necessarily going to happen, just because that is an overhead. But cycling through a subset of filters, I don't know how we're actually going to do it. And just to note your previous response about what's happening with the DFs, the decisions there will probably be happening last. So we're the SCOC, and note the SCOC is the preferred terminology for that group, not SCOC. So the SCOC we're going to define the footprints and the big sort of scale goals first, and then go into the nitty-gritty details of how we might schedule DDFs, how we might schedule overlap with DDFs versus Euclid, how we might, all of the balancing of the smaller sort of 1% issues will have to be kind of done at the next step. And so they haven't really been decided on. The dither, for instance, all of that. And maybe, as you say, the dither will probably only really be decided once we get commissioning data. And so there's going to be a lot of work that's going to be done through the next 2 years to kind of finalize everything.
And Franz, in terms of the DDFs, is there going to be some decision as to the amount of time the DDFs will receive in the first year? Because clearly that's going to set some global issues as to how much other sky you can cover and such.
Yes, and nothing has been concluded.
Nothing
So-
yet, sure, nothing yet.
Yeah.
But that will be something that we will know in the near term, is what you're saying.
We
We will know, did the deep drilling
probably
fields get a ton of time or only a little bit?
probably that decision won't be made. We haven't even started discussing it, and so
Okay.
I wouldn't expect to hear anything before December. At the very minimum,
Sure,
you will start
sure,
to hear
sure.
at the PCW. You will start to hear how we are condensing down on area of the sky, wide, fast, deep, galactic survey, etc. But the actual details of the DDFs, and even will the DDFs be all the same? They don't need to be, and probably we don't even want them to. We might want like each DDF to test a certain regime or a certain parameter space, and so that hasn't really been decided on. There aren't really any white papers that, or there's 1 or 2 white papers that kind of discuss that, but not in really of the detail we would like it to be. So it's something to consider, right? We may want them not to be uniform.
Okay, but we should know. I understand those technical details may wait, but in terms of the amount of time the deep drilling fields will be receiving, we should know that by end of 2021.
Maybe.
Okay.
Also,
Okay,
just
so-
to add, I think to Paulo's question, we wrote a cadence note also mentioning this issue of the simultaneity and the color changes on the effect of photometric redshifts. So that might be something to look at as well.
Thanks.
Okay, so we've got about 10 minutes left, and I realize I'm somewhat negligent and that I should have steered discussion to hosts before we lost people to time zone conflicts. So I posted some comments and questions from Amanda Banerjee in the Slack. We can certainly continue these discussions in the discussion session tomorrow and on Wednesday. However, we will have the same problem. So let me at least encourage people to start thinking about these, and maybe we need some side conversations in Slack or something of that.
Yeah, and Mara, did you have anything you wanted to present? I know you weren't able to do the full talk, but I thought you had mentioned you might have a couple of slides you wanted to share or something.
Yes,
Or are you
indeed.
good?
Yes. No, yes, you're right. So I have like a few slides that were explaining the title of my talk. And so if there were the time of the interest, that I can definitely show something related to photosys, but I can also do it tomorrow or Wednesday, whenever it is the time.
Why don't you go ahead? I think we have time for that. Let people think about hosts, overnight.
Okay, let me prepare the slides. It is really.
And Niel, while Mara's getting ready, Mara had asked when we're releasing the talks. My recollection is that it's hard to post on YouTube instantaneously. Yeah.
What do you mean releasing the talks?
We were going
posting
to
them.
make. Yeah.
Yeah, posting them.
Well,
Yes.
as promptly as I can. I might be able to do it today. I haven't actually received the email from Zoom yet about the first recordings from this morning as to whether I don't even have them yet. But as soon as I have them, I should be able to go in, do any small editing necessary, get them up to YouTube pretty quickly. That's my hope. Is that answering your question?
Yeah, perfect. Thank you. Okay, so then let me share the key slides that I had in mind for the talk. One of the reasons for not giving the talk is that I did not manage to be completely ready for Tunit for LSST. So just take directly the message that that's important for the discussion now, and it is strongly related to the SD fitting discussion that was done early today. So I am basing my experiments on the IFEDs. Probably have seen it in the splash last week. And what I'm interested in showing is the difference in the quality of the photometric redshift in the area that is in the red shape area and the one that is in the green. For those that didn't see the splash, these are 140 square degrees X-ray detected. So I'm speaking about X-ray selected AGN, not optically selected. To be true, some of the objects are also optical AGN, but this is not something that I can cover now. But the important point here is that depending on the area, we have a different kind of photometry. Namely, in the area here in red, we have the kids. So you have a U, G, R, I, Z, and then you have a deep Viking force photometry, the position of the optical, in addition to Galax and what else I'm using, and of course a WISE. And the WISE is coming from the deep photometry in LS8. And the area outside, you do not have the kids, but you have hyper supreme cam everywhere, and the hyper supreme cam is providing the Y. So combining the optical kids and the Y from hyper supreme cam, even if there are differences in the photometry, aperture, match in the photometry, PSFs, all what we have discussed, you can still have an idea what is happening when you compute the photosys using only optical bands. And I'm showing this because I'm a little bit worried, because when we were discussing about the photosys to be released to the community, everybody is focusing on providing photosys for galaxies so that everybody is getting a catalog that is science ready for making science ready, essentially, forgetting that if you have an AGN, even knowing that is an AGN, the photosys are going to be really limited just because you're using only optical. And what I'm arguing is that this should not be done. So as soon as an object is an AGN, it has to be flagged because the photosys are not reliable if you're using only optical bands, which is the plot that I'm showing here in the red in the right side. So in the left, you have the photosys, the best that I could manage with a CD fitting, using all this photometry on the kids area, knowing that the object is an X-ray detected, knowing that it is an extragalactic object, knowing that there is an AGN. Here, I was wondering whether the U-band is the one making the difference. So I got exactly the same photometry, but I took away the U-band. So already you see what happens when you do not have the U-band. The value that you have to look is the fraction of outliers on the top and the accuracy expressed as a sigma nmed. So you see already you increase the fraction of outliers. The sample is large, so it's not that it's a small number statistic. Here you have the one-to-one spec Z versus photosys, and in red, essentially, you have the outliers. The horizontal lines show you the systematics. And if I use only U, G, I, and Z and Y in the kids area, this is what you have. Essentially, is tossing a coin is giving you exactly the same result. And these are just the bright objects. If you go fainter in photometry, this effect is going to be less because I can show you, I don't know if I managed to be clear. Here I'm showing the fraction of outliers as a function of photometry. And you see that I'm also, so we are, there are two things to tell you. This is really becoming a talk, I'm really sorry. But you have as a function of photometry, X-ray flux, and redshift, and we are splitting the results for objects that are point-like, so we know that they are quasars, and objects that are nearby and they are extended. And essentially you see that, yeah, you have everywhere outliers, especially at the low redshift, because the hosts become really important. But what I wanted to say is that this is true if we are using SCD fitting, because if you use machine learning, again, going back to some of the talks this morning, actually, these are providing good results. So this is an attempt done with deep learning using only hyper supreme cam data, so even not the U-band, on the same objects that are from Rosita. And you can see that the quality is so in sigma is practically the same or a little bit better, and the fraction of outliers is not so bad. And again, look at the inside the kids area. And this is true for the quasars and the extended sources. So to make the short story is optical alone VSD fitting is extremely risky to provide to community, and we need to have multi-wavelengths data attached to our data, and at that point then SD fitting become again best, simply because there was not training at the moment. Probably if you train also with the other photometry, machine learning at this point is great again. If you want to provide only photosys using only photometric bands, then you have to go machine learning. And this is the short story that I wanted to give you today.
Okay, great.
Is there
Thanks,
somebody
Mara.
there? Oh, okay, yes.
Yeah, thank you. Okay, so I'll give people a minute or two to comment on that. I do want to wrap up in the next 5 minutes, just to maintain everybody's goodwill, because we said we would end at a certain time, and I'd like to do that. We've been on for a long time, but comments and thoughts on PhotoZ and the stuff that Mara just presented.
Yeah, my understanding so far is when we've reached out to the broader LSST photometric redshift effort and tried to say essentially what Mara's just said quantitatively, they've said, well, we are doing the LSST bands, and that's what we're doing. Is that a correct summary of the situation right now? I know Roberto, for example, has been communicating with these people some.
Yeah, so that was something that was mentioned in the last workshop, I believe. And yeah, that's the answer that we've been given.
They consider, sorry, go ahead, Roberto, then I can add.
No, I think that it might be, so at this point, it might be worth writing this on one of the reference letters to the arguing this point much more deeply, in the sense that it might just simply not be useful to not include any additional data. But yeah, we can talk more about that.
Yeah, so
Gordon, go ahead.
Now we were at the same meeting, and essentially what they were saying is that they cannot do everything, and they consider the adding of the other photometric points as signs that somebody else can do. And they simply wanted to provide to the community a basic photosys with parameters like stellar masses and such. As soon as they started to say that, we got scared. And so I would be actually proposing that either we manage to do something reliable, but if this is what we managed to do with the optical band alone, assuming we are using CD fitting, I don't think it is healthy for anyone to provide these photosys as soon as you know that the object is an AGN. And so what Roberto, we were saying that maybe the flag on the quality of the fit, assuming this is a galaxy, will be enough to alert the people that the object is an AGN, so they should not trust the result. But I wonder how many people are reading the README files by experience. And so I'm really scared.
Mm-hmm.
Yeah, and also a quality flag might be the most useful thing we could get out of the exercise, right? Something that tells us whether this looks like a galaxy or not, so we can, feed it as information into whatever we do later on.
Okay, so it sounds like there's an agreement that this is a potential issue. It could be another task force that we need to come up with, and certainly, want to make people aware that so-called the PhotoZ letters of recommendation are due September 30th, and I don't know that one from us saying, hey, we really need multi-wavelength data will have any impact, but it certainly will have no impact if we do not submit such a letter. So let's do so. Okay, anybody